Okay, hello and assalamualaikum everyone. I am Dr. Asad, Associate Professor in the Department of Computing, School of Computer Engineering and Computer Science. The title of my talk is Distributed Architecture for IoT Applications. So I simply modified this title as compared to specifically talking about the underwater IoT sensors or IoT smart farming, because there are some areas which we have been working on, like smart farming. So it's already been included in this presentation. Okay, so this is brief about me. So I'm associated with High Performance Computing Lab, and I'm IEEE senior member. And so basically, my perspective of looking into this problem is slightly different what you had in the yesterday talks. So I will mostly focus on distributed simulation aspect. So whenever we are working on typical problem like the data transmission in IoT sensors or how to perform the computation in cloud data centers, so we utilize these computing frameworks which are available online for the community. My other area of research is our cloud computing, Internet of Things, smart cities, and vehicular network and autonomous vehicles. Recently, we have been working on autonomous vehicles where we are focusing on resource sharing, how these vehicles can share resources for time critical tasks. And these are some of my citation index here from Google Scholar. Okay, so this is the overview of my talk. So this, as I mentioned, that it's all under the umbrella of distributed simulation. So I will start with the data centers, cloud data center, then we talk about the large scale data transfer, and then we talk about the scalability through IEEE standard, which is 1516, and then at the end we talk about the smart farming and software defined sensors. Okay, this is journal architecture. So whenever we talk about the IoT applications, more or less we are following the same architecture. So at the bottom there, they are the sensors, and then we have this network involved here. Most of the time, this network is the wireless network, and they actually the sensing the environment as well as actually they are acting as a relay nodes, transferring the data to the edge devices, and where we can filter out the data and move the raw data, and then we forward the data using a wired network to the data center. So typically speaking, so we have two locations where we can perform computations. The first one is the edge location here. The second one is the data center here. So if we place our model training at the edge location, so we have a limited data here because the edge location has a limited AOR as compared to the data centers. But when we want to transfer the data, bulk data from edge location to the data center, it is again a challenging problem. So I will start with the data center and move towards the IoT sensors. When we say the IoT sensors, so these days IoT sensors are software-defined sensors, which means you can modify their functionality. You can define new routing algorithms through over-the-air push software. So in that, I will discuss about this software-defined sensors. Okay, this is a computing tier, the cloud at the top, and then we have the fog tier, which is actually based on the intermediate devices. So it can provide computation up to certain extents, and then we have the edge devices. The devices are billions of devices at the edge locations. So this is a trade-off, right? So whenever we're designing an IoT applications, we have to decide where we want to train the model. Either we want to train the model at the edge location, fog node, and cloud data center. Here we'll get more computing resources, more GPU, more powerful resources. We can provision resources. But the thing is, if we talk about the delay critical applications, we are getting more delay as we traveling towards this cloud data center. Here we have the limited capacity, but the delay is minimal because it is close to the edge devices. Apart from that, there is another concept of niche computing, which is actually based on the devices. So now the devices are intelligent as well. They can initially filter out some data, they can perform some computation on its own. So we call it a niche computing, which is not here. Okay, so we started with the cloud simulator, right? So basically, the idea is like we were looking at this simulation frameworks, which allow us to simulate the cloud data centers and allow its connectivity with IoT sensors. So we started with this work and exploring the different existing simulators, which are very well known in the community. The cloud sim is actually very well known. It is developed by University of Melbourne, Rajkumar Boya. It is in Java. And then apart from that, we have also explored some other simulators. And based on that, we propose this CloudNet Sim Plus. So Cloud Sim is very well known in the community. The major problem in this simulator is like there's a lack of network stack. So there's The only thing they are using for message communication is storing the functions through their by passing the parameters. So there is no OSI layers there. There are no network stacks, so you cannot simulate the delay. You cannot simulate the packet drop. You cannot simulate the bit error rate, which is when we talk about the network are the main ingredients of that network. Apart from that, ICANN Cloud, this is designed for only for VM migrations, and these are some kind extension of CloudSIM. And with Cloud Analyst, this is designed for particular problems. So this is designed for VM migration, and it allows open source integration of this policy, which is based on which allow you to simulate the VM migration. So based on this, we came across this CloudNet simulation. The idea is actually we want the entire cloud data centers features in it, like a VM migration, SLAs, graphical support, and availability, language support, energy models. So these are the ingredients of data centers which we are incorporating in CloudNet and plus. Apart from that, it is also provide an API which allow you to integrate with this IoT sensors. So the data is generated from the IoT sensor, which is traveled through hop by hop and reach to the data centers. And the data center, you can perform the computations, right? So this is the starting point of our research. Okay. Okay, so this is the diagram of our CloudNet and plus. So we implemented a three-tier architecture. So this is a three-tier architecture. This is a core switch, and then we have the aggregate switch, and then top of the rack switch. These are the computing nodes, and when we have the 10 gig network here and 1 gig network here. So this simulator is designed on the top of OmNet++. So we have all the network functionality available in our simulator. The data is generated from the sensors, reached to this here, where we schedule it on the available computing node. So there is extensive network here, which actually act as a relay node and receiving the data, and based on the routing tables, they are forwarding the data to the data center. So this was our initial step. So looking into the integration of IoT with our cloud simulator. So this is the interface of our simulator. So this is the rack at the top of this is the top of the rack switches, and then we have some of the compute node connected with this switch. So this is aggregate switch, and these are the rack. This is a further exploration of this rack, and then we have this is the network layer, which has multiple connections from this coming from this rack, and then at the top of this layer. Okay, so based on that, our main objective is to analyze the energy, how much energy we are consumed by receiving the data from the sensors and executing inside the cloud data centers. So if you see the 75.6 kilowatt hour is consumed by the access switch, 10% is consumed by the aggregate switch, and core switch is 25.6% and consumed by the core switch. So the core switch actually receives the data from the IoT sensors, and based on that, the scheduler schedules those tasks to the available server, and the server actually computes those tasks, and these are the energy which they consume while executing those tasks which they receive from IoT sensors. Right. And then we have the intermediate switches, how much energy they are consuming, and then we have a computing server where we actually categorize based on their CPU energy consumption, memory, this peripheral, and motherboard. So this is actually more or less we are focused on the energy consumption of our servers and our network part. Okay, so after completing this work, so what are the lessons we learned? So these are the two main areas which we actually start further exploration on this. So large scale data transfer to central repository. So when we are talking about this IoT sensors which are generating data, and the data is actually traveled towards the data center, there are many intermediate nodes which actually consume too much energy. So we conclude that the typical network is not designed for this transferring of large scale data. Apart from that, there is energy dissipation because of intermediate nodes, and then there are transmission delays. So these two things actually motivate us to further explore this area. And the second thing is scalability. So we designed our simulator in OmNet++, but we came across to a certain point like if we only simulate data centers, we can simulate up to 1200 nodes. But if we include the IoT sensors, we can simulate up to 1800 nodes. So that is the limitation of this simulator. More or less, whatever simulator we have seen in our study, all the simulators have certain limitations based on the system we are using for the simulation purpose. So these two are our further steps to explore. Okay, so we start looking into the data migration between this edge network and then the cloud data center. The idea is like somehow the company has stored the data initially at the edge network, and the size of the data is reached to the terabyte or petabyte, and now they want to transfer the data to this cloud data centers, and there are intermediate nodes between this thing, right? Why they want to transfer the data to the cloud data centers? Because they want a global learning their model, right? So these are some of the statistics we got from the internet, like 100 terabyte over the internet. If you want to transfer, it will take 2 years. If 1 petabyte over the internet, 22 years. 100, 609 years, right? So these are the significant numbers, which means we cannot transfer our large scale data over the internet. So this is one of the challenging problems we had at that time. Then we further explore how what type of bandwidth we are getting in different subcontinents. Like America, we are getting 7.05, 37.12, 14.09, and this is about transferring of 20 terabyte in these continents. So if you see this Australia is 14 months, and Asia is 5.72 months. This is again a significant number, and we are talking about 20 terabytes only. Just to recall you, so nowadays, electric vehicle can generate 4 terabytes of data in half an hour. So you can understand how much data now we are generating and what are the limitations we have over here. And here we are only considering the upload time. Download time is not involved there. Okay, so then we start exploring what other communities or the cloud providers are doing for this work. So we came across this SETI project. SETI is search for extraterrestrial intelligence. So the idea is like their concept is like they are looking for the other intelligent beings out there. So they have the large telescope deployed at the Puerto Rico, which scans and collects the signals from there. And then the signals are actually, they collect the data from the radio telescope and write the data into the hard drive CDs, and then data is transmitted to the University of California, where actually they perform analysis and then pattern matching to identify if there is any other intelligent being out there. So they are not using the network, they are using the tape drive and they are using the hard drive. Okay, so this is one of the things, and then we look into the Amazon, what Amazon is doing, because in 2006, Amazon started actually pay-as-you-go model, which is actually, we can say, encourage the industry to move towards the cloud side, right? So what Amazon is doing, so they offer 3 types of data transfer mechanisms. They call it Snowball family. So AWS Snowball, Snowball Edge, and AWS Snowball Mobile. Right? So these are big size containers. When you want to transfer your data from your organization to the cloud data center, you have to request for this device. You have to register for the device by creating an import job. So once you get the device, you can connect it with your network, transfer the data, and after copying the data, you have to ship back this device to the data center, where the Amazon will copy your entire data to S3, so you can perform your machine learning analysis or whatever you want to perform there, right? So these two are the encouraging factors. So, based on this, we propose another framework which allows us to transfer the data from one location to another. The one thing we have noticed here is like, so these devices are very much limited, right? So if you can assume that 100, you get 100 requests for such devices. So these devices are only 10 or 15 in number. So probably you will get your turn after few months, right? So this might be a tedious task for the organization, right? So based on that, so these are some of the specs. So different devices support different terabytes. Some of them provide onboard computation. Some of them has the onboard GPU, so you can also use them for computation on the way. And these are some other specs for them for these 3 devices. Okay, so energy associated with communication through internet can be categorized as the user end and the network end, right? So now we are bifurcating this energy consumption in terms of user end and this network end. In user end, the energy consumption is 38%, whereas on this network end, the energy consumption is 62% of the entire energy. Which means the intermediate switches, router, repeaters, and the data center. So this is quite significant in numbers. Right? If we further focus, like if we want to transfer 20 terabyte data then 1 or 2.4 megawatts energy is consumed by the internet. So this is only we are talking about the internet. So we are not considering here the energy of the data centers, right? Okay, so to tackle this problem, actually, we came up with this idea like if we want to transfer data within certain range, which is connected to the road network. So why not utilize the ongoing electric vehicles or intelligent vehicles to carry your data, right? This is some kind of data center and want to transfer our data here because the data center usually keep a copy in a separate data center. So in case of disaster, they can recover your data from the different data centers. So then we propose there should be an edge locations on the way because we are not using a dedicated vehicle there. We are using the volunteer vehicles like the taxis, the people who actually commute from one city to another on daily basis or weekly basis. So they can take the data in their vehicles and they can transfer the data either at the edge location or at the nearby data center spot. So this was our main idea, and based on that, we actually build up a framework where we develop a controller which actually receive all the requests from this data center which want to send the data to the receiver data center, and the controller actually broadcasts the amount of data they want to transfer, and the nearby vehicle actually accept those requests and upload their data and start traveling towards their own journey. Like if they are going towards the offices, they will continue with their journey, and on their way, they can upload their data on the nearby edge location. Right? So in this way, the data actually move hop by hop and actually eventually reach to the data center. So this was our main framework here for traveling the data from the edge locations to data center or from one data centers to the second data center. So now that we have to actually do some kind of analysis, how do we select this vehicle? So we have to minimize read and write, right? So read and write means whenever we select a vehicle randomly, it may be take the data up to certain extent, maybe few kilometers. But our goal is to make sure that we select the vehicle which take the data near to the end location, right? So for that, we use actually taxi traces of Puerto Rico protocol. We got the traces of 1 year. And based on that, we use neural network to select the vehicle which are actually moving towards this destination node. Okay, so these are some of the statistics. The other statistics are available on this paper. So we actually see the data transfer in terms of size. If we increase the size from 10 terabyte to 40 terabytes, how much data we can transfer. So one is the ML scheme, which we use where we use neural network, and the second is non-ML. So where we actually utilize this random selection behavior. So you can clearly see in the 10 terabytes, we successfully transfer 90% of the data from this one node, from the source data center to the destination data center. Apart from that, we also perform some statistics analysis, like how much read and writes we are performing. Read and write means if the data is moved hop by hop, the more number of hops means more number of read and write, right? So in non-ML case, we have significantly reduced this number of read and write because we are selecting the vehicle based on their pattern because of their history. Yeah. Okay, comparing with the traditional internet, so 10 terabyte, 20 and 30 terabytes, so this much amount of minutes required for when we want to transfer this data over the internet. And in our case, ML, we are taking this 40 minutes, 67 and 125, right? So what gain we have is like 193% gain from comparison with the internet. Apart from that, the CO2 emissions, because of this intermediate node with read and write action performed between the hops and these vehicles actually drop the data on the edge location. So we actually measured how much CO2 emissions we are generating because of this transfer of data. Okay, so next step is actually as I discussed in the first part, we took two take-home lessons. One was the data migration, and second one was the scalability, right? So if we talk about the scalability and we have the sensors connected with the data center, we have a limited scalability, whatever simulator we are using, right? So we extensively analyze what kind of simulators are available and what kind of scalability they are providing. most of them are tightly coupled. Means you cannot split them. You cannot split them and run them on different systems, right? Because of that, you have a system limitations. Whatever system you have, you can simulate up to certain extent. So based on analysis, we propose another system which is actually based on a high-level architecture, which is IEEE standard 1516. It provides us the interoperability between different modules running on the different systems. So like this is the high-level architecture. This is a middleware which is running on a system. And apart from that, these are the physical nodes. This would be the one data center, and this would be the second data center, which are running on the different nodes. But still, they can communicate with each other in the form of public subscribe mechanism. Right. We adopted this and we moved towards the cloud, which is a Java-based development, and we want to actually make it a scalable version. So based on that, so these are the some of their modules, which we actually now, after incorporating this HLA layer between these modules, now these data centers can be run on different nodes, right? The data center is running on a different system, the broker fabric is running on a different system, and cloud information service is running on a different system. So previously, it was designed as a tightly coupled system. All these modules are running on a single system. And by incorporating this HLA layer, we have to ensure that these devices, these modules, now can run on different systems, but still they can provide you the same performance, same analysis, which they were providing you before. Right? Okay, so based on this knowledge what we got from our previous experiences, we move toward the smart farming. Like, so what if we want to simulate the smart farming setup? What framework, what facilities, or what protocols do we have at this time? So in our literature review, we came across like most of the work on smart farming is actually based on the actual devices. They are talking about the IoT sensors. They are getting the data from IoT sensors. But very limited work exists on distributed simulations because simulations are important. It helps you to analyze your protocol, your deployment, your message passing. You can also analyze the energy efficiency of your system. So this was the motivation. We took this problem. So we propose this architecture, which is actually based on multi-tier architecture. So we have a large-scale farm. In this farm, we have the sensors. Sensors are of different types. We generate data periodically, and then we have the UAVs, which actually collect the data from these sensors, and then we have the fog proper, right? So the fog proper actually define the paths for which UAVs collect the data from the farms, and then the data is gathered at this location by the fog proper, and which is further disseminated to the edge location for the processing, and later on it is moved to the data center. So this is internal architecture of our proposed framework. So we have the UAVs. UAVs have the constraint of energy, so they have a limited time. So after every seconds, we reduce their energy and see how much residual energy they have, so they can continue with their journey or not. And the broker is actually managing all these incoming tasks to the available resources for further computation. So when I say the computations, means like we are talking about in MIPS. MIPS is the million instructions per second. So we are not talking about a particular application. The task is coming in terms of MIPS. We are providing computation in terms of MIPS, and based on that, we analyze how much energy we are consuming at the data center, how much energy we are consuming at the intermediate nodes, and how much energy we are required to cover the entire region for smart farming. Okay, so this one is more or less similar, but this is ongoing work which we are actually focusing on the intruders. The sense UAVs are there, the spawns are there, they are collecting the data, but if somehow the intruders get into your system and try to manipulate your data, so how you can actually predict predict your data collection behavior or the path of the UAVs if some intruder get in and try to disrupt your entire framework. So this was the extension of the previous work, but this is ongoing work. Now we are focusing on intruder. So these are the results. Some of the results we got, like when we talk about the smart farming, the sensors are usually static, so they are relaying the data from one node to another. And the second option we have is to collect the data from the UAV. So how much energy we are getting in terms of simulation time, this is plotted here, and the packet delivery ratio in terms of UAV speeds, and this is plotted here. So this is again simulated in Omnet++. So we have network stack intent. Okay, so this is the last part. So as I mentioned, the software are now the sensors are now the intelligent devices. So we can actually modify their software on the go over the air. So instead, because why we want to update their software, because we want to modify the relay protocols. If we are not satisfied with the one relay protocol, maybe they are consuming too much energy. So we can push different kind of protocol or modules into that, right? But the problem is that when we talk about the smart farming sensors, so these sensors are usually fixed, right? So they are not moving. So the problem is little bit easy, flexible. So we took this problem and moved towards electric vehicles. So electric vehicles is also a sensor-based problem, but the challenge is more complex because the vehicles are actually moving, and we want to push the update to update their firmware. So in this case, we actually propose a SEECS-based framework, which actually based on the edge locations for fog nodes, and the fog node has a limited range, right? So they take the picture, take the snapshot of their intermediate AR, and based on that, actually they draw a complete topology diagram, which actually helps us to identify which vehicle is connected with which vehicle. So the idea is actually we don't want to actually broadcast this update to everyone because most of the vehicles may be already updated. So broadcast means we are consuming the network, and the network consumption means that we are limited the execution of other applications, right? So what we propose here is like the ASEAN controller will select one of the pivot vehicle, and the pivot vehicle will be selected based on their history, based on their direction, speed, or their firmware update version. And then they push the update to that pivot vehicle, which actually further update push this update to another vehicle. And this in this way they can build a chain from one node to another, and this chain go up to certain number of nodes. So this is actually a challenging problem because when they select this node, both these vehicles are moving. Sometimes they are moving in the same direction, and sometimes they are moving in the opposite direction, right? So sometimes we observe that the network failures has occurred if our selection is actually based on the random pattern. But if we select this vehicle based on their direction and some kind of history, we have improved how much efficiency in this proposed system. So this is the architecture of our work. Okay, so whenever the organizations like Tesla want to update their vehicles, they actually push their updates over the years. And they are doing it right now, but they actually recall all the vehicles in their vicinity and they start pushing this update over the air. So what we propose is like instead of calling these vehicles to this control unit to a central location, you can push the updates while they are moving around in the city. So the application is pushed through this application layer to the fog node where we have the SDN controller. It selects this pivot module. The pivot module actually selects this pivot vehicle, and it's how they select this pivot vehicle actually take a snapshot of the entire vehicle in its range. Based on that, it's create a topology on the runtime, and from that topology, it's take the most suitable vehicle, have a pivot vehicle, and then start disseminating the updates to that vehicle. The vehicle further select another vehicle within its range by applying some mechanism, and then this way we can transfer this updates from one vehicle to another. So these are some of the results we measured in terms of network convergence, how much network convergence, and network convergence is like how much time we are taking to maximize this convergence of these updates. We compared it with this ICNDD and TLDD. So this is actually in ICNDDs, they based on the clustering approach. So only the cluster head is selected, and the cluster head further disseminate one or two vehicles within its range. And this TLDD is based on the random selection through the fog node. Right? So in network convergence, based on this arrival rate, with increasing arrival rate, which means we are increasing the number of nodes in our simulations, and this is the results we are getting in terms of convergence. In this case, we actually introduce some kind of malicious vehicle because when we talk about this, the vehicles moving on the road, there might be some vehicles who are actually malicious or intruder in your system. They don't want to disseminate the update because they want to disrupt your network, right? So based on that, we still have a better convergence compared to the other instruments. Okay, so this is trustworthiness. So the malicious node is there. So we have to identify the trustworthiness of this vehicle. So we, based on how we computed that, so every vehicle is monitored at the fog node. So every vehicle has certain amount of time to forward this update to another vehicle. If during that period they do not establish a connection with another vehicle, we eliminate them from our network and we mark them as an untrusted vehicles. And based on that, we computed this trustworthiness and then effectiveness of our proposed framework. Okay, so that's all from my side. These are some of the references which we use, which I use actually in this presentations. If you have any questions.
One question. You talk about the previous farming one, some intruder stuff. You were saying that there is an intruder that is coming. So what do you mean by the intruder? Does it mean that another UAV we are talking about, or any object or dynamic stuff?
Okay, so in that case, we are talking about large scale farming, right? So large scale farming is like, so the farms are very large and it's, the owner is not the only one person. There is a community which actually hold a portion of the land. So they pool their resources to actually monitor their land, right? So they have the UVs which are coming from different owners. So there might be a scenario where one of the owners actually intentionally program their UVs to actually not forward or not like the correct right data from the farms. So this was a case study we took because it's not possible that everyone actually buy certain number of UVs to monitor the entire portion. So it is like the community effort. Any other question?
In general, what would be the size, minimum size to have this model of large scale farming?
At this model,
Sorry. In like, what would be the minimum size of the field to have this large scale farming, efficiently have this large scale farming?
it depends actually. In simulation, we are simulating actually around 100 by 100.
100 by 100 meters or
Kilometers. So this is common in western side. In Pakistan, it's not very common here. But mostly we are focusing on the other parameters. So this is not into consideration, but it's actually side. The idea is like we have a significant amount of land which we want to monitor, and how we can monitor. We can allow the community to actually contribute in terms of UAVs. So they can collect the data and upload the data to the HPA.
So in the last slide, we talked about the arrival rate. What do you mean by this?
So arrival rate actually, so we run the simulation with varying arrival rate. Arrival rate is like this 100 arrival rate means the 100 vehicles enter into our simulation per second. 200 is like we are increasing the size and we are looking into the statistics how we are getting. Because there could be an urban area, rural area, so like the give you the perspective of both sides.
Just one more question. Which simulation you are you using? Which simulation tool are you using?
It's different. Which one you're talking about?
For this large scale farming?
Large scale farming, we're using AnyLogic.
Logic.
AnyLogic.
What else are there?
Omnet. We started with an Omnet. We moved towards this AnyLogic, and we also use Python in one of this project. So it's moving around. Okay. Thank you.